Imagine this. You're living your life, making choices, experiencing the world as you know it. You feel like the one and only you, right? But what if that feeling, that solid sense of self navigating a single, continuous timeline, is just a beautifully crafted illusion? Buckle up, because we're about to dive into the mind-bending depths of quantum physics and explore a concept so wild, it might just change how you think about reality, your choices, and even who you are. Think of the vastness of space, then multiply that by infinity. Some theories in cosmology suggest we live in an inflationary multiverse, an endless ocean of universes, each like a bubble in a cosmic sea, and our universe is just one of them. Now overlay that with the bizarre rules of quantum mechanics, the physics that governs the tiniest particles of existence. Here, reality isn't always what it seems. It's fuzzy, probabilistic, and brimming with potential. And according to its mathematical language, that potential might just extend to you, countless versions of you, living out every imaginable possibility. Picture this. In one reality, you confidently walked into that job interview and landed your dream career. In another, gripped by a moment of doubt, you decided not to go, leading your life down a completely different path. Maybe in yet another, you never even saw this video, blissfully unaware of the quantum rabbit hole we're about to plunge into. And the possibilities don't stop there. Consider the truly unimaginable. A universe where you were born with a different talent, or in a different country, or maybe even one where the specific combination of events that led to your existence never actually occurred. These aren't just fantastical scenarios ripped from the pages of science fiction. They emerge directly, almost inevitably, from the equations that describe the fundamental nature of our universe at the quantum level. If reality isn't a fixed, singular path but a constantly branching tree of infinite possibilities, then the truly staggering question isn't if parallel versions of you exist, but rather, how many are out there? And what does that even mean for the you experiencing this moment right now? For centuries, our understanding of reality was neat, tidy, and predictable, governed by the elegant laws of classical physics. Think Isaac Newton's laws of motion, describing how a thrown ball arcs through the air, or how planets glide in their orbits. Classical physics painted a picture of a universe operating like a grand, intricate clockwork mechanism, where cause always led to a specific effect. If you knew all the initial conditions, the position and momentum of every particle, then, in theory, you could predict everything that would happen, from the next swing of a pendulum to the collision of galaxies. Reality was a single, unfolding timeline, a river flowing in one direction. But then came the quantum revolution, shattering this comforting certainty like a dropped glass. Scientists peering into the realm of atoms and subatomic particles discovered a reality that was anything but fixed. Instead of clear-cut paths, they found probabilities. Instead of definite locations, they found clouds of potential. At this most fundamental level, the universe seemed to be in a constant state of flux, with multiple possibilities existing simultaneously. Imagine a single electron. According to classical physics, it should be in one place at one time, moving along a definite trajectory. But quantum mechanics tells us that before we measure its position, it exists in a superposition of states, meaning it has a probability of being in multiple locations at once. It's not that we don't know where it is. It's that, in a very real sense, it is in multiple places simultaneously. This isn't just a quirky feature of the microscopic world. Quantum theory genuinely suggests that every quantum fluctuation, every interaction between tiny particles, and yes, perhaps even every decision you make could be a point where the universe subtly, or perhaps drastically, branches into different possibilities. You might not just be living one life. You might be a node in a vast, invisible network of realities, with countless variations of your existence playing out in parallel. But if this is true, and the math seems to support it, a natural and deeply compelling question arises. Where are these other versions of you? Why don't we bump into our alternate selves at the grocery store? And perhaps most profoundly, why do we only experience one seemingly singular reality at a time? What is it about our perception, our consciousness, that seems to lock us into this one particular branch of the infinite possibilities? At the very heart of quantum mechanics lies one of its strangest and most unsettling principles: superposition. We touched on it briefly with the electron example, but let's delve a little deeper into why it's so crucial to understanding the potential for multiple realities. Unlike the objects we encounter in our everyday world, a coffee cup is either on the table or not. You're either reading this or doing something else. Quantum particles don't play by these rules until they are observed or measured. Think of a coin spinning in the air. Before it lands, it's neither heads nor tails. It's in a superposition of both possibilities. Only when it lands and we look do we see one definite outcome. Now, imagine this not just for a spinning coin, but for the fundamental building blocks of the universe. This isn't just a bizarre theoretical claim. It has been repeatedly confirmed through some of the most elegant and mind-bending experiments in physics. The most famous of these is undoubtedly the double-slit experiment. Imagine firing tiny particles, like electrons, one at a time towards a barrier with two narrow slits in it. Behind the barrier is a screen that detects where the electrons land. If electrons behaved like tiny marbles, you'd expect them to go through one slit or the other, creating two distinct bands on the screen behind the slits. But what actually happens is far more peculiar. The electrons create an interference pattern on the screen, just like waves of water passing through two openings and interfering with each other. This suggests that each electron is somehow going through both slits simultaneously. It's behaving like a wave, spread out in probability. However, the moment scientists try to measure which slit an electron actually goes through, by placing a detector at one of the slits, for example, the wave-like behavior vanishes. The interference pattern disappears, and the electrons start behaving like those tiny marbles again, going through one slit or the other. The act of observation seems to force the electron to choose a single path, collapsing its superposition into a single, definite reality. This experiment raises a truly chilling question. If fundamental particles can exist in multiple states at once, until we look, could the same principle apply to larger systems? Could it apply to collections of particles that make up molecules, cells, and eventually, even you? Could you, right now, be existing in a multitude of potential states in different realities without even being aware of it? Is your current experience just one collapsed possibility out of an infinite array? To truly grasp the bizarre implications of quantum mechanics for our understanding of reality, the brilliant physicist Erwin Schrödinger proposed a now iconic thought experiment in 1935, Schrödinger's cat. It's a bit macabre, but it brilliantly highlights the paradox. Imagine a sealed box containing a cat, a radioactive atom, a Geiger counter, and a vial of poisonous gas. The radioactive atom has a certain probability of decaying within a specific time frame. If the atom decays, the Geiger counter detects this decay, which in turn triggers a mechanism that breaks the vial of poison, killing the cat. If the atom does not decay, the cat remains alive. Now here's the quantum twist. According to quantum mechanics, before anyone opens the box to observe the system, the radioactive atom exists in a superposition of two states, decayed and not decayed. Because the fate of the cat is directly linked to the state of the atom, the cat, entangled with the atom's quantum state, is also in a superposition of states. It is, in a very real quantum sense, both alive and dead at the same time. This isn't to say the cat is some kind of zombie creature. It's a thought experiment designed to illustrate the absurdity of applying quantum superposition to macroscopic objects. Our everyday intuition tells us that a cat must be either alive or dead, not both. The act of opening the box, of observing the system, forces the atom to choose a state decayed or not decayed, and consequently, the cat becomes definitively either dead or alive. The superposition collapses into a single, classical reality. While this seems like just a quirky thought experiment, it reflects a profound and unresolved issue in quantum mechanics: the measurement problem. Why does this strange dual-state property seem to apply so readily to subatomic particles, but not to the larger objects we encounter in our daily lives? Where is the boundary between the quantum world and the classical world we perceive? Furthermore, this thought experiment begs the question: if larger objects, even hypothetically a cat, can exist in multiple states until observed, what happens when you make a choice? When faced with two options, does your quantum self also exist in a superposition, exploring both possibilities simultaneously until your conscious decision collapses you onto one path? And if so, what happens to the other you, the one who took the road not taken? Does another version of you continue on that different path in another reality? The answer to this question leads us to one of the most mind-blowing and controversial ideas in modern physics: the many worlds interpretation. In 1957, a young physicist named Hugh Everett III proposed a radical, and at the time, largely dismissed idea to solve the measurement problem. What if quantum superposition never actually collapses? What if, instead of a single reality being chosen when a quantum event occurs, the universe itself splits into multiple parallel realities, each one representing a different possible outcome? This revolutionary concept became known as the many worlds interpretation, MWI, of quantum mechanics. Under MWI, every time a quantum event with multiple possible outcomes takes place, and these events are happening constantly at the fundamental level of reality, the universe doesn't just pick one outcome. Instead, it branches, creating a new, separate universe for each possible outcome. Let's bring this down to your life. Imagine you're offered two different job opportunities. According to the standard interpretation of quantum mechanics, like the Copenhagen interpretation, which we'll discuss later, when you make your decision, the wave function describing your potential futures collapses, and you end up in the reality corresponding to the choice you made. But under the many worlds interpretation, things play out very differently. When you're faced with that decision, the universe splits. In one branch, a version of you accepts job offer A and experiences the subsequent reality. In another branch, an almost identical version of you accepts job offer B and lives out that alternative future. And if there were other possibilities, like you deciding not to apply for either job, then yet another branch of reality would emerge where that version of you never faced the decision at all. This branching process happens constantly, at every quantum interaction, leading to an almost unfathomable number of parallel universes, each one slightly different from the others, representing a different sequence of quantum events and the resulting macroscopic outcomes. Unlike the alternate realities often depicted in science fiction, these aren't necessarily universes you can hop between. They are considered to be entirely separate and non-communicating timelines, all unfolding simultaneously within the overarching multiverse. Your consciousness, according to some interpretations of MWI, follows one specific branch, giving you the subjective experience of living a single, continuous life. But here's the truly mind-blowing implication. If reality is constantly branching in this way, then right now, at this very moment, there could be countless versions of you living out different possibilities. Some of these versions might be living lives wildly different from yours. Perhaps you're a famous musician in one universe, or a renowned scientist in another. Others might be living lives almost identical to yours, differing only in some tiny, seemingly insignificant quantum event that occurred moments ago. If this idea is blowing your mind right now, you're not alone. It's a concept that challenges our deepest intuitions about reality and selfhood. But before we go further, take a moment to let that sink in. The possibility of an infinite number of you, spread across an infinite number of universes, each living out a unique variation of your life. If the many worlds interpretation is correct, then the existence of an infinite number of you across countless parallel realities seems almost unavoidable. But this leads to a profound and unsettling question. In this vast spectrum of possibilities, which version of you is the real you? Consider two parallel universes. In one, you made a life-changing decision that led to immense success and happiness. In the other, you took a slightly different path, perhaps driven by fear or uncertainty, and now you face challenges and regrets. Are both of these versions equally you? Does the you reading this now somehow hold a privileged position? Or are you simply one instance among an infinite multitude, none more real than any other? Quantum mechanics, with its inherent probabilistic nature, suggests that you might not be a single, fixed identity, but rather something akin to a probability wave, constantly collapsing into momentary certainties with each quantum interaction and each decision you make. Every choice, every observation you make seems to solidify one particular version of you, while the infinite other potential versions continue to exist and evolve in their own separate timelines. The implications of this are deeply personal and potentially disorienting. Somewhere out there, a version of you might be living your wildest dreams, achieving everything you've ever hoped for. Equally, somewhere else, a version of you might have made every mistake you've managed to avoid, facing consequences you can barely imagine. And in the most extreme scenarios, somewhere in this vast multiverse, a version of you might never have existed at all, the specific chain of events that led to your birth never having occurred. This challenges our very understanding of selfhood and identity. What does it mean to be you, if there are countless near-identical copies living different lives? Are we merely observers, our consciousnesses somehow locked into one specific branch of reality, experiencing only a tiny sliver of our potential existence? Or could consciousness itself be something more fundamental, perhaps even entangled across multiple versions of existence in ways we don't yet understand? The deeper we delve into the mysteries of quantum mechanics, the more reality starts to resemble not a single, solid truth, but rather a vast and ever-expanding collection of possibilities, each one just as real as the one we currently inhabit. Quantum mechanics, despite its strangeness, works incredibly well in practice. It's the foundation of much of modern technology, from lasers to smartphones to medical imaging. However, when it comes to actually interpreting what these equations mean about the nature of reality itself, the community of physicists is deeply divided. Over the past century, several competing interpretations have emerged, each attempting to explain the bizarre behavior of quantum particles and the perplexing connection between the quantum and classical worlds. Yet, none of these interpretations have been definitively proven, leaving us in a state of profound uncertainty about the very fabric of existence. Let's take a look at some of the main contenders in this ongoing debate. The Copenhagen interpretation. This is arguably the oldest and most historically influential interpretation, largely attributed to Niels Bohr and his colleagues in the 1920s. The Copenhagen interpretation posits that reality exists as a set of probabilities, described by the wave function, until a measurement is made. The act of observation forces the wave function to collapse into a single, definite outcome. The Copenhagen interpretation doesn't really explain how or why this collapse occurs. It simply states that it does. This reliance on a seemingly mysterious observer effect has been a source of discomfort for many physicists over the years. What constitutes a measurement? Does it require a conscious observer? These questions remain largely unanswered within this framework. The many worlds interpretation, MWI. As we've already discussed, proposed by Hugh Everett III in 1957, MWI offers a radically different perspective. It rejects the idea of wave function collapse altogether. Instead, every time a quantum event with multiple possible outcomes occurs, the universe splits into multiple parallel universes, each representing a different outcome. We, as observers, become entangled with one of these branches and experience only that particular reality. MWI neatly avoids the need for a mysterious observer-driven collapse, but does so at the cost of postulating an infinite number of parallel realities, a concept that many find difficult to accept. Pilot wave theory, also known as Bohmian mechanics, developed by Louis de Broglie and later refined by David Bohm, this interpretation offers a deterministic view of quantum mechanics. It suggests that particles are not just waves or probability distributions, but actual point-like particles with definite positions at all times. These particles are guided by a hidden pilot wave, the wave function, which determines their motion. Pilot wave theory restores a sense of classical predictability to the quantum realm, but it does so by introducing these hidden variables, the pilot wave itself, which have never been directly detected and remain a controversial aspect of the theory. The truly shocking truth is that, despite decades of intense research and increasingly sophisticated experiments, there is currently no known experimental way to definitively confirm which of these interpretations, if any, is the correct one. Each interpretation can successfully explain the mathematical predictions of quantum mechanics and account for the results of experiments. They all fit the data, yet they offer wildly different pictures of the underlying reality. And yet, despite this fundamental lack of understanding about what quantum mechanics truly means, it underpins a vast array of real-world technologies that we rely on every day. From the global positioning system, GPS, in your phone, to the magnetic resonance imaging, MRI machines used in hospitals to the burgeoning field of quantum computing, we can manipulate the quantum world with incredible precision. But we still don't truly understand the fundamental nature of what's happening beneath the surface, at the very foundations of reality. As the renowned physicist Sean Carroll eloquently puts it, the many worlds interpretation isn't just some wild, outlandish idea. It's a surprisingly natural and logical consequence of the equations of quantum mechanics if you take them at face value and don't try to impose the extra assumption of wave function collapse. But as we've seen, not everyone agrees, and the debate continues to rage. Despite nearly a century of intense discussion and groundbreaking experiments, physicists remain deeply divided on what quantum mechanics actually tells us about the fundamental nature of reality. The equations themselves are incredibly successful, powering technologies that have transformed our world. But the meaning behind those equations, the underlying picture of reality they paint, remains stubbornly elusive. We're at a scientific standstill, not due to a lack of data, but because the data seems to support multiple, fundamentally different interpretations. One of the biggest hurdles in resolving this crisis of interpretation is the issue of mathematical equivalence. As we touched on earlier, the major interpretations, Copenhagen, many worlds, pilot wave, and others, all predict the exact same experimental outcomes. No matter how cleverly we design our experiments in the quantum realm, the results always align with the predictions of quantum mechanics itself, but they don't definitively point to one interpretation over another. It's as if we have multiple maps of the same territory, each drawn with different symbols and legends, but all ultimately guiding us to the same destinations. Physicists have relentlessly tried to break this deadlock with increasingly mind-bending experiments. Quantum eraser experiments have shown that future measurements can seemingly influence the past behavior of particles, challenging our intuitive understanding of causality. Delayed choice experiments suggest that the decision of whether to observe a particle as a wave or a particle can be made after the particle has already passed through the experimental setup, hinting that a particle's nature might not be fixed until the moment of measurement. Non-locality studies have definitively proven the existence of quantum entanglement, where two or more particles become linked in such a way that they share the same fate, no matter how far apart they are, exhibiting instantaneous correlations that seemingly defy the speed of light. Each of these experiments provides further confirmation that the quantum world operates in ways that are utterly alien to our classical, everyday intuition. But instead of resolving the debate over interpretation, they have often only deepened the mystery, revealing even stranger and more counterintuitive aspects of quantum reality. Some physicists, like Sean Carroll, argue that the many worlds interpretation is the most logical and parsimonious explanation, as it doesn't require the ad hoc assumption of wave function collapse. Others vehemently insist that quantum mechanics, as we currently understand it, is incomplete and that there must be some deeper, hidden structure or mechanism that we haven't yet discovered, perhaps along the lines of pilot wave theory. And then there are those who take an even more radical stance, suggesting that the entire debate about an objective quantum reality might be misguided, and that reality itself is, in some fundamental way, shaped by our observations. So, where does all this leave us? We stand at the edge of one of the greatest scientific mysteries of all time. We possess a theory, quantum mechanics, that is incredibly successful at describing and predicting the behavior of the universe at its most fundamental level, and we can even build advanced technologies based on its principles. Yet, we still don't have a clear and universally accepted understanding of what that theory truly tells us about the nature of existence itself. Until we do, the fascinating and often bewildering battle over the interpretation of quantum reality will undoubtedly continue. What if the fundamental problem isn't with quantum mechanics itself, but with how we are trying to interpret it? A radical and increasingly influential idea, known as quantum Bayesianism or cubism, pronounced cubism, suggests that the entire debate about an objective, observer-independent quantum reality might be fundamentally missing the point. According to cubism, quantum mechanics doesn't provide a description of some underlying, objective reality that exists independently of us. Instead, it's viewed as a powerful and remarkably accurate tool that individual observers can use to manage their own beliefs and expectations about the universe based on their past experiences. In other words, the wave function, that central mathematical object in quantum mechanics that describes the state of a quantum system, isn't seen as a real physical entity. Instead, it's interpreted as a subjective representation of an observer's degrees of belief about the possible outcomes of their future measurements. This means that reality, as we perceive it, isn't something external and fixed, waiting to be discovered. Instead, it's deeply personal and contextual, shaped by what we as individual observers can know and predict based on our interactions with the world. Every measurement we make on a quantum system doesn't collapse some pre-existing reality. Rather, it updates our own personal probabilities and beliefs about the system's state and the likely outcomes of future measurements. If this sounds more like philosophy than physics, that's because it is. Cubism deliberately shifts the focus away from ontology, the study of what exists, and towards epistemology, the study of what can be known. It doesn't attempt to answer the question of whether particles are really waves or particles before they are observed. Instead, it argues that such questions are ultimately meaningless because our only access to reality is through our own subjective experiences and the information we gain through our measurements. Reality, from this perspective, is an evolving first-person experience that is inherently tied to the observer. This idea has profound and potentially unsettling implications. If the fundamental nature of reality depends, at least in part, on what we as observers can know and believe, then the universe might not exist as a single, absolute, objective structure that is the same for everyone. Instead, it could be more like a shifting, ever-changing narrative, one that varies from observer to observer, based on their individual histories and interactions with the quantum world. Could this mean that reality is entirely subjective, a construct of our individual minds? Or is there still some deeper, objective structure underlying quantum uncertainty, even if we can never directly access it? If cubism is right, we may never be able to definitively answer that question, because all we ever have is our own unique perspective, our own set of beliefs and expectations that we update through our experiences. It's a perspective that emphasizes the active role of the observer in shaping their own understanding of reality. As we've explored, quantum mechanics offers a multitude of interpretations, each attempting to provide a coherent explanation for the bizarre behavior of the quantum world and its implications for the nature of reality. The many worlds interpretation proposes a universe constantly branching into countless parallel realities with every quantum event. The Copenhagen interpretation suggests a reality that only becomes definite upon measurement by an observer. Pilot wave theory posits hidden variables guiding the behavior of particles in a deterministic way. And cubism argues that quantum mechanics is fundamentally about our subjective beliefs and experiences, not an objective external reality. Despite decades of intense research and theoretical development, no single experiment has been able to definitively prove which, if any, of these interpretations is the correct one. Each has its own strengths and weaknesses, its own philosophical implications that either resonate with or deeply trouble different physicists. For example, the many worlds interpretation elegantly eliminates the seemingly arbitrary and ill-defined process of wave function collapse. Every possibility is realized, just in a different branch of the multiverse. However, this comes at the cost of accepting the existence of an infinite number of unobservable parallel universes, a concept that strikes many as extravagant and untestable. Pilot wave theory offers a return to determinism, a comforting idea for those who find the inherent randomness of standard quantum mechanics unsettling. But it does so by introducing hidden variables that have so far remained undetectable, raising questions about their fundamental nature and whether the theory is truly more explanatory. The Copenhagen interpretation, while historically dominant, has been criticized for its vagueness regarding the role of the observer and the exact mechanism of wave function collapse. And cubism, with its focus on subjective experience, challenges our deeply ingrained intuition that there must be an objective reality independent of our perception. The deeper we delve into the quantum realm, the stranger reality seems to become, forcing us to confront fundamental questions about what it even means for something to be real. Is reality observer-dependent? Is it fundamentally deterministic or probabilistic? Are there limits to what we can know about the universe? These are not just technical questions for physicists. They touch upon some of the oldest and most profound inquiries in human thought. For nearly a century, the brightest minds in physics have grappled with the meaning of quantum mechanics, yet the debate over its interpretation remains unresolved. It's not for a lack of trying. Quantum mechanics has been subjected to more rigorous experimental testing than perhaps any other theory in the history of science. Its predictions have been confirmed with astonishing accuracy across a vast range of phenomena. The core of the problem isn't a lack of data. It's the fact that the different interpretations, despite their radically different underlying assumptions about the nature of reality, all make the exact same predictions for any observable outcome. This mathematical equivalence creates a fundamental barrier to experimentally distinguishing between them. It's like having multiple different stories that all perfectly explain the same set of clues, leaving us unable to definitively say which story is the true one. Attempts to break this interpretational deadlock have led to some of the most conceptually challenging and technically demanding experiments ever conceived. Weak measurements attempt to gently probe quantum systems without fully collapsing their superposition, hoping to catch a glimpse of some underlying reality that is hidden from standard measurements. Quantum eraser experiments, as mentioned before, continue to baffle scientists with their suggestion that the act of measurement can retroactively influence the past state of a particle. Delayed choice tests, pioneered by John Wheeler, further underscore this strangeness, hinting that a particle's fundamental nature might not be decided until long after it has seemingly made a choice in an experiment. Non-locality experiments continue to confirm the bizarre interconnectedness of entangled particles, defying classical notions of space and time. Each of these experiments, while providing valuable insights into the counterintuitive nature of the quantum world, has ultimately failed to definitively confirm one interpretation over the others. Instead, they often seem to deepen the mystery, revealing even more layers of quantum strangeness that challenge our classical understanding of how the universe works. The results of these experiments raise profound and unsettling questions. Can the future truly influence the past? Does reality only spring into definite existence when it is observed? Is there a hidden order or structure beneath the apparent randomness of quantum events that we have yet to uncover? Every potential answer seems to lead to even more fundamental and perplexing mysteries about the nature of reality itself. The deeper scientists dig into the quantum realm, the more it seems like an intricate and perplexing riddle, one that may not have a single, definitive answer that we can all agree upon. The very act of trying to understand it forces us to confront the limits of our classical intuition and the very nature of scientific explanation. Quantum mechanics isn't just an abstract scientific puzzle confined to the ivory towers of academia. It poses a direct and profound challenge to our most fundamental understandings of free will, personal identity, and the very nature of existence. If the many worlds interpretation is indeed a correct description of reality, then every decision you make, every quantum event that occurs in your brain, could be causing a branching of reality. This would mean that with every choice you face, a new universe splits off, one where you chose one option and another where you chose differently. This raises a profound question about the nature of free will. Are you truly making choices, or are you simply navigating an infinite and ever-expanding web of predetermined possibilities, with each version of you experiencing one specific branch? In this view, free will might still exist as a subjective perception, the feeling of making a choice, but the ultimate outcomes, all possible outcomes, already exist in the multiverse. Every possible version of you already exists somewhere across this vast cosmic tree. On the other hand, if reality follows something closer to the Copenhagen interpretation, where conscious observation plays a crucial role in collapsing the quantum wave function and bringing about a single, definite outcome, then your awareness might play a far more fundamental role in shaping the reality you experience. Are you simply a passive observer in a pre-existing world? Or is your very act of observation actively participating in the unfolding of reality, selecting one possibility from a multitude of quantum potentials? Even more deeply unsettling is the question of personal identity in a quantum multiverse. If there are truly infinite versions of you existing across countless parallel realities, which one is the real you? What defines your sense of self in this vast landscape of possibilities? Are you a unique and indivisible individual, or just one fleeting expression of underlying quantum probabilities, a momentary ripple in an infinite ocean of potential selves? Some interpretations of quantum mechanics suggest that what we call the self might be nothing more than a temporary and localized collapse of a vast and interconnected wave function, a momentary certainty in an otherwise fluid and constantly branching reality. No matter which interpretation of quantum mechanics ultimately proves to be the most accurate, or even if a completely new understanding emerges, one thing is undeniably clear. This field of physics forces us to radically rethink everything we thought we knew about existence, choice, consciousness, and the fundamental nature of reality itself. It's a journey into the deepest mysteries of the cosmos and our place within it. If reality consists of a single, linear timeline, as classical physics suggested, then meaning in life can often be found in uniqueness. Every event, every choice, every experience is singular, a unique thread woven into the fabric of your individual story. The path you take is yours and yours alone, and its significance stems in part from that exclusivity. But what happens to this sense of unique meaning if we live in a multiverse, where infinite versions of us exist across countless branching realities? If every possible choice you could make is being made by another version of you in a parallel universe, does your individual existence still hold the same weight? Does your personal journey still matter if it's just one among an infinite number of similar, yet different, journeys? One fascinating perspective suggests that meaning in a multiverse doesn't necessarily derive from uniqueness, but rather from awareness. Your particular path, your specific experiences, and the choices you make in this particular branch of reality may not be exclusive to just this version of you, but they are nonetheless real and significant for the you experiencing them. Just as some interpretations of quantum mechanics emphasize the role of observation in defining reality, perhaps meaning itself is determined by your conscious awareness of the path you are currently on. The joys you feel, the challenges you overcome, the connections you forge. These are all part of your unique experience within your current reality, regardless of what other versions of you might be experiencing elsewhere. Strangely, this idea resonates with ancient philosophical and spiritual traditions. Some interpretations of Eastern philosophies like Buddhism and Hinduism describe reality as an interconnected web of possibilities, where all choices and all outcomes coexist in a state of potentiality. The emphasis is often on the present moment, on the awareness of your current experience, rather than on the ultimate uniqueness of that experience. Even Western existentialism, with its focus on individual freedom and responsibility, suggests that meaning is not an inherent property of the universe, but something we create for ourselves through our choices and actions, regardless of whether those choices are replicated elsewhere. If the multiverse is indeed real, then your existence is not a singular event, a fleeting spark that occurs only once. Instead, it's a presence, a pattern of consciousness that is spread across an infinite number of realities, each one offering a different perspective on the spectrum of your potential. Perhaps the question to ask isn't, what is my one true purpose in a singular universe? But rather, how do I choose to experience this particular reality that I currently inhabit? Maybe meaning isn't found in being the absolute, one and only version of yourself, but in fully embracing and engaging with the version of yourself that you are right now, in this moment, in this unique unfolding of possibilities. It's about finding value and significance in the experiences, relationships, and choices that define your current reality, knowing that even if other paths exist, this one is yours to navigate and to make meaningful. So, what do you believe? At the heart of quantum mechanics lies a profound paradox, a fundamental uncertainty that forces us to confront the very nature of reality. Is the universe a single, objective structure, operating according to deterministic laws, a grand cosmic clockwork ticking away in a predictable fashion? Or is it an endless, branching web of possibilities, where every quantum event, every decision, gives birth to a multitude of new realities, each just as valid as our own? The truth, as we've seen, is that science hasn't definitively decided. The equations of quantum mechanics work with breathtaking accuracy, allowing us to understand and manipulate the universe at its most fundamental level. Yet, those same equations don't come with a built-in instruction manual for their interpretation. They don't tell us which picture of reality, the single, deterministic one or the infinite, probabilistic one, is the correct one. Some physicists find solace in the idea that reality only truly comes into being when it is observed, suggesting a deep and perhaps unavoidable connection between consciousness and the fabric of the universe. Others find the elegance and completeness of the many worlds interpretation compelling, even if it necessitates the existence of an unfathomable number of parallel worlds. And still others suspect that our current understanding of quantum mechanics is incomplete, that there's a missing piece of the puzzle, a deeper theory waiting to be discovered that will finally resolve these perplexing questions. But perhaps this very uncertainty is what makes quantum mechanics so powerful and so profoundly important. It challenges us to step outside the comfortable confines of our classical intuitions, to rethink what we consider to be real, to question whether the world is as solid and predetermined as it often seems, and to embrace the possibility that our understanding of existence is still in its infancy. So let me ask you again, what do you believe? Do you lean towards a singular, deterministic reality where every event follows a fixed chain of cause and effect? Or are you more inclined to accept the mind-bending idea of infinite versions of yourself living out every conceivable possibility in a vast multiverse? If this journey through the strange and fascinating world of quantum reality has blown your mind and sparked your curiosity, then you definitely won't want to miss what we have coming up next. We're planning to dive even deeper into the related mysteries of consciousness, the enigmatic observer effect, and explore the intriguing possibility of how your own mind might play a role in shaping the very reality you experience. So make sure you hit that subscribe button and turn on those notifications, because some of the strangest and most profound discoveries about the universe and our place within it are still ahead of us. Stay curious, stay open-minded, and most importantly, stay healthy. We'll see you in the next video.